do this. In lesson 1, we talked about air patterns, and in lesson 2, we talk about how water moves in patterns across the earth. This is a pretty cool photo that shows, you'll notice that these gray areas are the actual land, and all this color is actually the speed of the water moving around. So you can see how there's powerful currents up in here going this way around the equator, which kind of makes sense because remember in the last lesson we talked about the Coriolis effect and where the Earth is spinning the fastest, right? And you have all those, the wind patterns are moving, like this, all kind of towards the equator, and you see how you have a lot of movement near the equator, kind of where they all meet. So, this starts off with, why does floating garbage tend to build up in certain places in the ocean? And so this is actually talking about these giant garbage patches that totally exist in the ocean. You can go to them. Some of them are, like, I think the one in the Pacific Ocean is supposed to be about the same size as Texas. So, and there are areas of the ocean that are just, if you're on a boat, there's just garbage everywhere floating in the ocean. So why do you think that? Take a second to think about it if you want. But why is that? Well, if you go back up here, you can kind of see a good idea. If you look at this picture, you might notice that there are certain places that are in the ocean, but there's not a lot of color, which means that there's not a lot of movement, right? This area kind of in here is pretty dark. In here, this is pretty dark. Up over here, the poles, up near the poles, down here, doesn't look like anything was being measured down here actually. But, we've got over here, there's less movement in these areas, right? So you go down, and lo and behold, look at that. They're the same, right? We've kind of got these patches. You can't really see this one because they didn't include the whole world in that direction, but over here, right? They're in the same places. So why does garbage collect there? It's because there's no currents to move anything around. So the water is more still. And so it kind of collects. So here, hopefully you see that this says, what patterns do you see in the movement of the ocean surface? Hopefully you see that it's stronger in some other places. There's lots of this swirly motion, right, which you might remind you of the whole Coriolis effect, and when I talked about in the last lesson about how, like when you look at sinks, how the water spins in a certain direction. And why do you think that there's so much movement in the ocean? Well, spoiler alert, there's a bunch of movement in the ocean because the Coriolis effect, right? Remember, the Earth is spinning this way, and so that causes the liquids and the gases to want to kind of move like in this type of a pattern around the equator, and also the pressure and temperature differences, just like with wind, will cause the water to move around. So we call this stream-like movement of ocean water, and a regular pattern is called an ocean current. So when you hear people talk about ocean currents, they're talking about these kind of patterns. Like you can see how there's a really strong kind of pattern like this right here. That's an ocean current. So here we have two little pictures. This is surface winds and surface currents. And if you kind of compared both of these, right? Remember in the last lesson we talked about how there are, there's these prevailing winds, which are winds are moving generally in one direction. And you might see how there's a lot of movement in the wind, particularly when it gets around the continents. And that's because, just like with wind moving around cars and wind moving around signs and trees, all this landmass will cause the wind to change and move around a little bit in comparison to the ocean when there's nothing stopping it in its way. But if you compare this and this, you'll find that there's a lot of similarities in how the wind is moving and how the ocean currents move. And number 5 says, what patterns do you see when comparing the global surface winds with the global surface currents in these maps? And if you kind of look at them, they're mostly moving in the same direction, right? Look at this. See, you have these counterclockwise circles, Up in the northern hemisphere, you have these clockwise type circles. And if you go up here, we have clockwise movement. We have counterclockwise swirls. So they're mostly moving in the same similar directions. More of the sun's energy is received near the equator than near the poles. This uneven warming causes, this would be pressure differences. Pressure differences, right? Because it's warming the air in the atmosphere. The pressure differences cause wind. This is from the last lesson 1. And as the wind blows, energy is transferred from the wind to the ocean. The energy transfer causes the water to move in the surface ocean currents. Okay. Factors that affect surface currents. So I can actually mention these already, but I mentioned what affects the surface currents are the currents right along the kind of the surface of the ocean, opposed to the ones really, really deep down. But we talked right here about how wind affects them, right? You can see that with these maps. The wind pattern affects the surface currents. Also, the continents, right? You can see here, the water's moving. A lot of this is the same patterns as the wind, but the wind can kind of more easily go over the land. Not more easily, it can go over the land. Water can't just go over the land. It's got to go somewhere. So the water goes this way, and then some of it goes up, some of it goes down when it hits the land. So obviously the land is deflecting. They call this continental deflection, and that refers to the change in the direction of currents as they meet continents. So if you go back up here, you can see how there's places where the currents are just really steady, moving along for a long time, and then all of a sudden they hit a continent and it's got to go somewhere. So the California current travels. The California current south. Highlight. Let's go. Highlight for me. South. From where the North Pacific current is deflected by North America, the California currently eventually turns to the west. And this is talking more about the Coriolis effect and Earth's surface flow in huge circular patterns called gyres. And those are due to the Coriolis effect, same as the wind. Those gyres are kind of like those small. You could see them really good in like these pictures, these gyres. You're probably familiar with that pattern mostly from hurricanes. Yeah. What do you notice on the map about the pattern of gyres in the northern hemispheres as compared to the gyres in the southern hemispheres? I kind of mentioned this in lesson 1, talking about wind, and a little bit earlier, but in the northern hemisphere, they are moving. In the northern hemisphere, it's clockwise, and the southern hemisphere, it is counterclockwise due to the Coriolis effect. That you can kind of think about on your own. Explain sea surface temperatures. So the sea surface temperature at the point labeled east is something. the sea level surface temperature at the point labeled west is something. What are you supposed to write here? Maybe just the temperature. Okay, so that would be the temperature. I'm not sure what this wants us to put here, but this is, well, the west is green, right? And so that's maybe, I don't know, 16 degrees? Put 16 degrees. Maybe you could say green here too, but the east is, it's like orange right here. So that's more like 26. The points east and west are about the same latitude, meaning they're about the same. See, they're both 35 degrees north, so they're both the same distance from the equator. So they receive about the same amount of solar energy. Explain why the points east and west have different ocean temperatures. So why do they have different ocean temperatures? Well, if you go back up here, you can kind of see how you have these different patterns where this North American one is because the winds and the continent, right, and how the patterns are moving. You have this cold water moving south, but then you have these warm, because it's moving, right? You have the air and it's near the equator and it's going up in this direction, right? It's going in a clockwise direction, so you have warm air coming up. Whereas in this one, you have water that's going in the same direction, but it's coming from more the north, and so this water is getting colder, and so it's getting colder as it goes towards the equator. So that's why you have cold air coming down this way, while in this one you have warm air going up. Exploration 2, modeling deep currents. This is a cool video I put in the work for this. I put a link to a video where you could see this, and in this one, it explains it more. So I'm going to kind of skip over this, but to go through it real quick, right? If you look at these two pictures, this is before and this is after. And in this example, the colors have mixed, and in this one they haven't. Maybe a little bit in the middle. Well, why is that? Well, that's because remember that cold air is more dense and the warm air is less dense. So warm air should be, or warm air and liquid or water is less dense, so it floats on top. So they have these little pieces of film in between the warm air and the cold air, and when they pulled the film out, in this case, right, the warm air was already on the top, so it just stayed floating on the top, and the cold air was on the bottom, so it stayed on the bottom. But in this one's case, they were flip-flopped, right? And so all this warm air wanted to, like all the warm air wanted to rise up, and all the cold, sorry, not air, water, and the cold water wanted to go down. And so they mixed, and they made this the purple color. So we're going to look more at this. This talks about the density of ocean water. And the main takeaway from this paragraph is that the average salinity of all the oceans is about 35 grams per liter, but ocean water has a range of salinity. Salinity is the amount of salt in water. So the higher salinity of ocean water it is, the more dense it is. So more salty water equals more dense. And so here we have water at a temperature, so this is measuring density of water according to the salinity and temperatures. So water at a temperature of 10 degrees Celsius has a density of about, so this is this one's measuring temperature, as you can see right here, temperature. And this one's measuring the salinity. And then they're both density. So this is a 10 degrees. At 10 degrees, where are we at? We're at about here. So about 1,000. This would be 1,000 kilograms per meter cubed and which means that a cubic meter, this means that a cubic meter of water, so if a cubic meter would be like a meter stick wide, a meter stick deep, a meter stick high, a giant chunk of a square of water, it'd weigh 1,000 kilograms. So 14. Water at a temperature of 25 degrees has a higher or lower density than water at 10 degrees. So here's 25, and it's right here. And this density is lower than it is. So 25 degrees is lower. As the temperature increases from 15 degrees to 30 degrees, so from 15 to 30 degrees, the density of water increases. Yeah, see, again, so 15, this is a little bit weird because it's, decreases. Right, you're going from, this is describing going from 15 to 30, and the density is falling, it's going down, it's decreasing. Here is a graph for salinity. Water with a salinity of 20 grams per liter has a density of, so 20 grams per liter is here. So that's about, 1,013. Kilograms per meter squared. I'm not going to write that as kilograms per meter squared. And water with a salinity of 34 grams per liter is higher or lower than the density with 20. So 34 is here-ish. 34 is like here. 20 is down here. And so it has a higher density. As the salinity increases from 0 to 40, the density of water, right, the density of water is going up. It increases. So what's the point? Changes in temperature and changes in salinity. So what this is showing is that the temperature and the salinity of water both change the density of water. So as temperature goes up, the density of water decreases, and as salinity increases, or the amount of salt in the water increases, the density increases. So when rivers flow into the ocean, the salinity of the ocean water would decrease because you're adding fresh water from the rivers, right? Rivers are fresh water. So they're adding fresh water to salty water. So it's going to decrease the salinity of it because the river adds fresh water. In an area of the ocean where a lot of evaporation but little precipitation happens, the salinity of water is likely to decrease. Therefore, the density is likely to, the salinity is decreasing. So the salinity is going down, so the density would also be going down. So the salinity is also decreasing. What this is describing, like you're in the middle of the ocean, and so lots of water is evaporating, but it's not raining there. So you're getting less water, but the salt isn't leaving with the water, so the water would be more salty. And here we're talking about the formation of deep ocean currents. So the density of ocean water will increase if the water becomes colder or if the salinity increases. If this happens, ocean water at the surface can become denser than the water around or below it, and the denser water sinks. And the downward movement of the water is what is causing deep ocean currents. And the deep ocean currents are the more regular currents within the ocean because they're not affected as much by the wind. They're more affected by like the continents and the salinity and things like that. Write the labels provided in the proper places in the diagram to explain the model. A surface current flows towards the pole. Oh, this is sideways. Here we go. The equator. This is confusing. See, this is north. So this is like the north pole up here, and this is the equator, and so the south pole would be that way. So a surface current flows towards the pole. This one goes right here. Surface flow, and then water sinks and forms a deep current, that would be here, right? So the water is going up towards the pole, and it gets cool, and it sinks, and then it goes back down towards the equator, right? Because remember, the equator is warm, so the water is getting warm here, and it's going up towards the pole and sinking. So, and this kind of talks about some of the factors that affect deep currents, and so the Coriolis effect affects deep currents. But a good example that you could see from here is, what's one of the reasons why the water gets cold up here? Well, one of the reasons it gets cold is because it's getting farther away from the equator, so there's less solar energy up at the top. But what else happens at the North Pole? Water freezes. And when water freezes, it doesn't take the salt with it, right? So as some of the water freezes, the water becomes more salty because the salt is left in the water. It doesn't get frozen with the ice. So that is more salty water, and that also makes it more dense. And so the water sinks down again. What process in the Mediterranean Sea might explain why the water level of the Mediterranean did not increase, even though all the surface currents were flowing into that sea? Oh, well, so this is just kind of describing, you have a bunch of, in this picture, right, you've got, basically what they're describing is all the surface currents are flowing into the Mediterranean Sea. You've got surface currents going in here, surface currents, all the surface currents are going into the Mediterranean Sea. So why doesn't the Mediterranean Sea keep getting like bigger? And the point is because it's going into the Mediterranean. The surface currents are going in, but the deep ocean currents are going out. So what processes in the Mediterranean Sea might explain why the water level of the Mediterranean did not increase? It's, that's the one I was just answering. Okay, exploration 3. Relating ocean circulation and the flow of energy to matter. So, I've been talking quite a bit, so I'm going to try and hurry this up. So, oceans make up a larger part of the hydrosphere because 97% of the Earth is water. Explain how Earth subsystems are interacting in each photo. So, A. In A, we have the biosphere, plants and animals, and the hydrosphere. In B, we've got the hydrosphere and the geosphere and the biosphere. And here we have like all of it. It's, here's people, the biosphere, we've got the geosphere, the hydrosphere, the atmosphere. It's all working together. Convection currents in the ocean. So this is just talking about how there are convection currents in the ocean, ta-da, just like in the atmosphere, right? Liquids and gases, they all have convection currents. So deep currents move towards the equator. That would be the bottom one, right? Because we have deep ocean currents and they're going towards the equator. And then surface currents move towards the pole. That would be up here. Because here we have surface currents and they're going towards from the equator to the pole. Using what we've read and observed in the diagram, describe the path of a molecule of water in a convection current in the ocean. So a convection current in the ocean, let's start at the equator. So at the equator, you got a molecule, a water molecule. Hi. I'm a water molecule. Not to scale. Okay, the water molecule is getting warmer because it's near the equator, so it gets warm. And so it's traveling along in its current till it gets to the pole. It gets to the pole, and the pole has less energy from the sun, so the molecule cools off, gets more dense. So it falls down to the bottom of the ocean, and now it's part of a deep ocean current traveling along back towards the equator. And then once it gets to the equator, right, because kind of all the other hot molecules are moving in this convection cell, it's being drawn up towards the warmer area. we're just getting more energy. Global ocean circulation. What's happening with this picture? The model below shows all the overall patterns of currents. It does not include the ocean currents. So this picture that you can't see, but you'll be able to see it, it has these little pictures and it talks about, these are describing what's in the picture. So you could read those if you want. I'm remembering what the picture says. In your school or community, there may be patterns of circulation that you can observe as a group of people move around during the times of different day. So in the past, we've talked about, patterns of school. We've always been in school. So a pattern that we've seen, patterns of circulation would be like, people getting dropped off and picked up for school. Flow of energy. It's talking about how the flow of energy is affected by things. So 25 is the greater temperature differences between objects, the more quickly energy is transferred. Which location would energy be transferred more quickly? So this is saying, if you have something that's really hot and really cold, the energy transfer happens more quickly than if you have something that's just like warm and lukewarm, or warm and a little cold. So what we're looking for here is the biggest temperature difference. So here, 5 degrees, this is 5 degrees apart. 2 degrees and 10 degrees, this is 8 degrees apart. And this is 0 degrees apart. So it would be B, because that's the greatest temperature difference. And the cycling of matter. And this is talking about how the cycling of matter is important. We talked about this a lot with the previous lesson 1, about how matter is cycled through the air, but it's also cycled through the water, right? We have gases and carbon dioxide and oxygen and organisms and all of this, garbage, all the stuff that's in water, all the stuff that's in the oceans, all the stuff that's in rivers, all the stuff that's in lakes, that gets cycled around through the water cycle. This is a big giant diagram showing the carbon cycle, for example, and how that's an example of things that move around, right? We have carbon in the atmosphere. It's used by trees in photosynthesis. More carbon is released through volcanoes. Fossil fuels and people breathing things out put carbon in the atmosphere. It goes into the ocean through organisms, right? Animals die. It puts carbon in the soil. These are just like the cycle of carbon, right? But you can see how in the cycle of carbon, water, all these things here are happening with organisms and things related to water. So the water cycle is a big part of the carbon cycle, as an example. And this says, describe at least 2 effects of the Earth system that might happen if ocean circulation stopped. Explain your reasoning. So if I go back up here and use this for ocean circulation, let's just imagine this is ocean circulation. First of all, you wouldn't have lots of fossil fuels, because fossil fuels is from organisms dying in the ocean. You wouldn't have a lot of the carbon in the atmosphere that gets used by plants in the ocean and animals in the ocean. So there would be more carbon dioxide in the atmosphere. The Earth would get warmer. So yeah, there's 2 examples. All right, well, that's it for lesson 2.